Section: Introduction. In this section, we explore the concept of fine-tuning large language models, LLMs, to enhance their performance in various tasks. Fine-tuning involves adjusting the models to follow specific instructions and exhibit desired behaviors while eliminating undesired ones. However, fine-tuning very large models can be costly in terms of memory and computational resources. To address this issue, various parameter-efficient fine-tuning (PEFT) methods have been developed to reduce the number of parameters and memory usage required for fine-tuning. One popular PEFT method is low-rank adaptation, LoRA, which suggests that the changes made to parameter matrices during fine-tuning have low-rank properties. This means that the updates can be represented by a low-rank decomposition, reducing the memory and computational requirements significantly. Unlike LoRA, our principal singular values and singular vectors adapter, PiSSA, focuses on approximating the original weight matrix directly, rather than just the updates. By utilizing singular value decomposition, SVD, on the pre-trained model's weight matrix, PiSSA divides it into a principal matrix and a residual matrix. The principal matrix is trainable, while the residual matrix remains fixed, allowing for faster and more effective training. In the realm of related works, parameter-efficient fine-tuning, PEFT, strategies like partial fine-tuning, soft prompt fine-tuning, nonlinear adapter fine-tuning, and linear adapter fine-tuning have been proposed to adapt large language models for specific tasks while minimizing memory and parameter requirements. Each strategy has its own strengths and limitations, with linear adapter fine-tuning, such as LoRA, being widely adopted for its ability to efficiently fine-tune models while maintaining their original architecture. Section Summary. In this section, we introduce the concept of parameter-efficient fine-tuning, PEFT, as a solution to the high computational costs associated with fine-tuning very large language models. We discuss the low-rank adaptation, LoRA, method, which reduces the number of parameters and memory usage by approximating weight updates with low-rank matrices, maintaining model performance while significantly decreasing resource requirements. Additionally, we present our principal singular values and singular vectors adapter, PiSSA, method, which diverges from LoRA by directly focusing on the low-rank characteristics of pre-trained model weights, enabling faster and more effective fine-tuning by initializing adapter layers with principal singular values and vectors. Section: Method. In this section, we present our principal singular values and singular vectors adaptation method. We follow the insights of intrinsic SED, which suggest that pre-trained models have a low intrinsic dimension. Our method, PiSSA, calculates the singular value decomposition, SVD, of matrices W within the self-attention and multilayer perceptron, MLP, layers. The SVD of a matrix W is represented as W equals U, CDOT, text, diag, S, CDOTV, T, where U and V are the singular vectors with orthogonal columns, and S contains the singular values arranged in descending order. The top R singular values are considered the principal ones, denoted as S_R, while the rest are the residual values, denoted as S_R. The principal singular values and vectors are used to initialize the injected adapter A and B, while the residual values and vectors are used to build the residual matrix. By introducing PiSSA at the start of training, we ensure that the model's capabilities are not compromised. The adapter AB captures the primary capabilities of the pre-trained model, and fine-tuning it mirrors the process of fine-tuning the entire model but with fewer parameters. Compared to LoRA, which initializes the adapter with noise and zeros, PiSSA benefits from a more efficient initialization that leads to better generalization performance. PiSSA shares many advantages with LoRA, such as the ability to fine-tune a model with fewer parameters, reduced memory consumption during training, and easy deployment. For storage efficiency, we can choose to store the low-rank matrices A and B instead of the dense parameter matrix delta W. By utilizing PiSSA for fine-tuning, we can quickly adapt a pre-trained model to different downstream applications by assigning different sets of A, B. In our experiments, we compare PiSSA, LoRA, and full parameter fine-tuning on various tasks. We find that initializing adapters with principal singular values and vectors leads to superior performance. PiSSA outperforms LoRA in terms of convergence speed and alignment with training data under the same parameter configurations. Additionally, we demonstrate that the fast SVD technique helps PiSSA strike a balance between initialization speed and performance. We conduct our experiments using the Alpaca implementation strategy with specific optimizer settings and training configurations. The experiments are carried out on the NVIDIA A800SXM4 80G GPU. Section Summary. In this section, we introduce the principal singular values and singular vectors adaptation method, PiSSA, which leverages the intrinsic low dimensionality of pre-trained models by computing the singular value decomposition of matrices within self-attention and MLP layers. By initializing adapters with principal singular values and vectors, PiSSA outperforms other methods like LoRA, demonstrating faster convergence and better alignment with training data, while maintaining the original inference speed of fully fine-tuned models. The experiments conducted showcase that PiSSA's approach of directly fine-tuning a model's principal components leads to superior performance on various downstream tasks, offering a balance between initialization speed and performance through the fast SVD technique. Section: Verifying the importance of principal singular values and vectors. In this section, we verified the importance of principal singular values and vectors by investigating their impact on fine-tuning performance. We initialized adapters in Llama 2-7B, Mistral 7B v0.1, and Gemma 7B with principal, medium, and minor singular values and vectors. These models were fine-tuned on the Meta Math QA dataset and evaluated on the GSM 8K and Math datasets. The results showed that initializing adapters with principal singular values and vectors consistently led to lower training loss and improved accuracy on both validation datasets for all three models. This demonstrates the effectiveness of fine-tuning model parameters based on principal singular values. We then evaluated the performance of PiSSA and LoRA across different ranks from 1 to 128. The training was done on the Meta Math QA dataset, and validation on the GSM 8K and Math datasets. PiSSA quickly converged at the start of training, while LoRA initially experienced a period where the loss did not decrease. Throughout training, PiSSA consistently maintained a lower loss compared to LoRA. Increasing the rank showed that PiSSA achieved similar fitting to the training set as full parameter fine-tuning with fewer parameters. PiSSA outperformed LoRA with the same number of trainable parameters and even surpassed full parameter fine-tuning as the rank increased. This approach of using principal singular values and vectors improved model robustness. A comparative analysis of PiSSA, LoRA, and full fine-tuning across various tasks showed that PiSSA outperformed LoRA and most full fine-tuning methods on all models and tasks. We plan to extend this comparison to more models and tasks in the future. To speed up the decomposition of the pre-trained matrix W, we use the fast SVD algorithm by Halko et al., which introduces randomness for an approximate matrix decomposition. Comparing fast SVD with traditional SVD, we found that fast SVD had significantly faster computation time with lower initialization error. As the rank increased, fast SVD remained efficient compared to SVD. Increasing the NITR parameter in fast SVD reduced the error and approached the training loss of models initialized with SVD.